Hi, this is Babak. In this video I'm going to talk about mathematical induction from theory points of view. This is the first video that I am going to talk about mathematical induction. In the coming videos I will talk about different variants of mathematical induction. Of course, my emphasis in these videos are not problem solving. Even though, of course, I will give you examples so that you realize why other variants of mathematical induction would be useful. Okay, so today I want to talk about two very important principles regarding the set of natural numbers n. So I will use letter n as is common for the set of natural numbers, and I will assume that the set of natural numbers starts from 1. So 1, 2, 3, etc. So well-ordering principle, WOP for short. Every non-empty subset of the set of natural numbers has a least element. So what does it mean? It means that if I choose any subset of the set of natural numbers so that it is not empty, then A contains a least element. So what does it mean? It means that there exists an element, say A, in A, such that for all other elements, say A prime in A is less than or equal to A prime. This A is called the minimum of this set, and I will write it as minimum of my set A. Okay? And it doesn't matter if this is a finite subset or an infinite subset. If you accept the well-ordering principle, you need to always you know that this is always the case. As soon as I have a subset from the set of natural numbers which is not empty, existence of the minimum element is guaranteed by the well-ordering principle. There is also another famous principle regarding the set of natural numbers n, and that's called principle of mathematical induction, PMI for short. Okay. Let me discuss about the content of this principle now. So assume that P of n be a predicate involving, so here B is repeated 2 times. So let Pn be a predicate involving the natural number n with the following properties. So what do I mean by a predicate? So predicate here, P of n, is a declarative sentence which contains a variable here n. Okay, for example, I can say that n is an odd number. Okay, so this is a declarative sentence. It is declaring something about this variable, but it is not a proposition or a statement yet. Because if I ask you evaluate the truth of this proposition, you will not be able to answer that, because we don't know if n is indeed an odd number or not, because we don't know the value of n. But as soon as I replace n with a number from the universe of discourse, so let me take the set of n to be the universe of discourse, it means that the set that all my variables are coming from that set. If I choose this as the universe of discourse, and if I replace n with, say, 2 from the universe of discourse and read this sentence, 2 is an odd number, then it is a proposition, it is a statement, and in this case it's a false statement. Okay, so a predicate is a declarative sentence containing one or more variables. Here I'm just talking about one variable coming from the set of natural numbers as the universe of discourse. So that it turns into a proposition if that variable is replaced by any element from the universe of discourse. Only then I can evaluate its truth value, true or false. That's the meaning of a predicate here. But now assume that you have a predicate with 2 very important properties. The first property is that P of 1 is true. It means that if I go in my predicate and replace the variable n with the first natural number 1, when it turns into a statement, that statement is a true statement. Another property is that if my statement is true for a particular choice of the variable n, say k, if that is true, then it is guaranteed that p for the next number is also true. If my predicate enjoys these two properties, then principle of mathematical induction claims that Pn is true for all natural numbers n. Actually, it's better to say asserts that it's true for all natural numbers n. Okay? In this video, I want to show that these two principles are actually equivalent. So it means that if you accept WOP, this automatically implies PMI. Or if you assume PMI, it implies WOP. So these are two equivalent statements regarding the set of natural numbers n. Okay? Okay, so let me just prove the first one. I want to go from WOP. I'm assuming WOP is true, and I want to show that PMI is a logical consequence of this assumption. Okay, so let me write proof here. What I want to do is this. I am assuming that WOP is valid. I want to show that this will imply PMI. This is the first step. Okay. So I would say let the set A be defined in this way. The set of all n's in the set of natural numbers such that the statement P for those values n is a false statement. Okay, so this is my definition. I am defining a set in this form. I am saying that go and choose those numbers from the set of natural numbers so that when you replace the variable in your predicate with those numbers, you get a false statement. Okay, I'm assuming that WOP is true. I want to show that PMI is also true. So if PMI is going to be true, the claim in the PMI, the assertion in the PMI is that Pn is true for all natural numbers. So it means that this set should turn out to be 0. So this is my goal. This should be the empty set. I want to show that this set is the empty set. Okay? We show that A is equal to the empty set. And I use proof by contradiction. Assume that this is not the case. Case and A is not empty. Okay? Now that you are saying that A is not empty, I also know myself that A is a subset of n. This is based on the definition of A. A contains elements from the set of natural numbers with extra property. So definitely this is a subset of the set of natural numbers. And now because at this stage I'm assuming WOP to be a true statement, so I can use it. So I will use it here. I would say WOP implies that A has a minimum element. Has a minimum. Okay? So then I would say that let A be the minimum of my set. What does it mean? When you say that A is the minimum of my set, it means that A belongs to the set A. Yes? So A belongs to the A. And then this implies that now that you are saying that A is an element of A, so it means that it satisfies these two conditions. Firstly, A is a natural number. Secondly, P of A is a false statement. So this is the consequence of this when you say that little a is the minimum of the set capital A. Okay. Now what I want to show is that this number A, this minimum, is definitely greater than 1. It's not equal to 1. Why is that the case? Because you know that P1 is true. Okay, so A cannot be equal to 1. If A is equal to 1, then this statement tells you that P of 1 is false, but I'm assuming that P1 is true. Okay, so since PA is false and P1 is true, A is not equal to 1. And since A is a natural number, A should be greater than 1. So we know that A is greater than 1. This is something important here. Okay, now when A is greater than 1 and A is a natural number, we can conclude that A minus 1 is still a natural number. Yes, A is a natural number greater than 1, so if I subtract 1 from it, it is still a natural number. Okay, on the other hand, you know that A minus 1 is strictly smaller than A. And on the other hand, A is the minimum of my set. So what does it mean? This means that this element cannot be in my set. Because if it is in my set, it is a contradiction because it is definitely smaller than A. A is my minimum, so it cannot be in my set. So this implies that A minus 1 does not belong to the set A. There are two reasons that might give rise to this statement. I know that A minus 1 is not in A. So either this should not be true, or this should not be true, or of course both. But we know that A minus 1 is a natural number. So the reason that A minus 1 does not belong to A is because P of A minus 1 is not false. Yes? So what does it mean? Is not false means true. So P of A minus 1 is true. Now I want to use the second assumption about my predicate P of n. I know that P, so let me write it in this way. I know that A minus 1 belongs to n. I know that PA minus 1 is true. Okay, so according to the second assumption regarding my predicate, it means that P of that number plus 1 is also true. So this means that P of A minus 1 plus 1 is true, but PA minus 1 plus 1 is nothing except P of A is true. Okay, but this is contradiction because here we realize that P of A is a false statement, and then we also concluded that P of A is a true statement. Okay, this contradicts P of A is false. Okay, now we prove that PMI implies actually WOP. So let me write proof. I want to show that PMI implies WOP. Okay? To this end, I would define a special predicate. So I would say let P of n be the following predicate. Here I'm talking about the set of natural numbers, so I will not emphasize over and over again these numbers, these variables are coming from the set of natural numbers, okay? So let P of n be the following predicate. Every subset of n, the set of natural numbers that contains the natural number, so I don't write that, contains n, has a minimum. Yes? So this is a predicate. It contains one variable n. But now I want to show that this statement, this predicate that I have written here, satisfies the first and the second property in the principle of mathematical induction. Okay, first let us go here. I want to show that P1 is a true statement. How should I do that? So what is P1? P1 means read your predicate, but replace the variable of your predicate with that value here, 1, and see that this statement that is produced in this way is true or false. Okay, so let me read P1. So every subset of n that contains 1 has a minimum. But this is trivially true, yes, because 1 is the minimum of the whole set of natural numbers. So it is clear that if I choose a subset from the set of natural numbers and that subset contains 1, that 1 itself is the minimum of that subset. So this is clear that this predicate is true if I replace the variable n with 1. So P1, let me just write it here, P1 is true. Now let us see what is the next one. Assume that k is a given natural number. So I would say let k be a natural number such that P of that k is true. So namely, what does it mean? It means that every subset of n that contains k has a minimum. Okay, so let me change my color here. Assumed to be true. Okay, now we show that pk plus 1 is true. So how should I show that? What is the meaning of pk plus 1? Let me read it. Pk plus 1 means every subset of n that contains k plus 1 has a maximum. So we want to show that every subset of n that contains k plus 1 has a minimum. So I would say let A be a subset of a subset of n that contains k plus 1. Okay, so let me write this with green here, emphasize these sentences. A is a subset of n. We also know that k plus 1 belongs to A. Okay, this is the short form of what I have written in English sentences. Okay, we prove that A has a minimum. I consider two cases. I would say that if 1 belongs to A, I am done. If 1 belongs to A, then 1 is the minimum of A. and we are done. So we assume that 1 does not belong to A. But we still want to show that even in this case, A has a minimum. I define a new set for you. I would say let B be the set of all natural numbers like X, but not all of them, having this property that if I add 1 to that, it belongs to the set A. So let B be this subset of the set of natural numbers. Okay, we know that, so let me write it in this way. We know that K is a natural number, yes? So we know that K is a natural number, and we know that K plus 1 belongs to A, yes? This is exactly what I have written here. Then this means that K belongs to B, yes? Because this K satisfies this condition. It also satisfies this condition. So it means that K is in the set B. Okay? But then B itself is a subset of N. Yes, because it contains those elements of the set N with an extra property. So this means that B is a subset of N. So I found a set B which has K in it and is a subset of N. And then you read, we have assumed that this statement is true. Every subset of N that contains K has a minimum. So this means that I can conclude from these two that B has a minimum. So I would say let little b be the minimum of this set that we just confirmed its existence. Okay, now what we can do, we want to show that, let me write, what is the meaning of B is the minimum of B? So this means that definitely B belongs to B. So this means that B is a natural number and B plus 1 belongs to A. This we know. Okay, my claim is that this B plus 1, which we confirm to be inside A, is the minimum of this set A. Okay, how should I prove this? So we show that B plus 1 is the minimum of A. How should I show this? I would say let A be an element in my set. We prove that A, B plus 1 is less than or equal to A. Yes, because if you want to show that B plus 1 is the minimum element of your set, you need to show that that element is smaller than any other element in your set. So what I have done, I have chosen a typical element of my set, and I want to show that this B plus 1 is less than or equal to that generic element from my set. If I show this, then I am done. Okay. Now let me ask you, so you know that 1 does not belong to A, and you know that A belongs to A, and you know that A is a subset of N. So this means that definitely A is bigger than 1. Okay, so this means that A minus 1 is also a natural number. Okay, A minus 1 is a natural number, On the other hand, when you add 1 to it, it becomes A, which is in your set A. So this means that this A minus 1 satisfies this condition and also this condition. So this means that A minus 1 belongs to the set B. But what is little b? Little b is the minimum of capital B. So this means that A minus 1 is greater than or B. Let me repeat. B is the minimum of your set. A minus 1 is an element of your set. So it means that this element is greater than or equal to the minimum element. So this means that A is greater than or equal to B plus 1, or equivalently B plus 1 is less than or equal to A. And that is exactly what we wanted to show. Yes, here we wanted to show that B plus 1 is less than or equal to A. Okay, so far we showed, let us review what we have done. Here I defined a predicate for you here, a predicate regarding the natural number n, and I was able to show that P of 1 is true, and I also was able to show that if P of k for some natural number k is true, pk plus 1 is also true. Because here I'm assuming that the principle of mathematical induction is valid, so it means that immediately I can conclude this. I can conclude that this predicate that I defined is true for all natural numbers n. So what does it mean? Let me write it here. So therefore, I was able to show that for all so let me write for every natural number n, every subset of n that contains n has a minimum. Oh, sorry, has a minimum. So this is the true statement. We now know that this statement is a true statement based on principle of mathematical induction. Now I want to show this WOP is also valid. So what does it mean? It means that I would say let A be a non-empty subset of n. We show that A has a minimum. Okay. Now, because A is not empty, this means that it contains, there is an element in n, because A is also a subset of the set of natural numbers, such that n node belongs to A. So A is a subset of n that contains the natural number n node, yes? Therefore, so let me write it in this way. This implies, let me give this statement a name, star. A star implies that A has a minimum. And I am done. So I was able to show that WOP implies PMI, and then I showed that PMI implies WOP. So it means that these are two apparently different principles but logically equivalent principles regarding the set of natural numbers. Okay, I hope that this video was useful for you. Below the video I will put the link to the PDF file of these notes, as well as some links to some of my lectures regarding the mathematical induction. In those videos, my emphasis is on problem solving, not the theory part. Okay. Until the next video, be safe and goodbye.